Welcome to another tutorial of Proflan YouTube channel. In this video, we're going to have a discussion on how to work with stationary waves, especially how to work out the wavelength of a stationary wave. We shall also work out the wavelength and the length of the tube when you are given some more information regarding stationary waves. Remember that stationary waves are formed when a progressive wave is reflected and it travels in the opposite direction. We are told that there is a string of 1.2 meters which is attached to the wall and fixed on the vibration generator. So meaning when this generator provide the vibrations will travel through the string to the wall. Upon reaching the wall, the progressive wave is reflected back in such a way that we are going to have a wave reflected back like that. Remember, the original wave was moving in that direction. Upon reaching this particular point, is reflected from the wall, and then the wave travels back like that. Then the two waves are going to superpose. Superposition is going to take place. These two waves are having, this is the incident wave, and this one is the reflected wave. So upon superpositioning on each other, then we are going to have a stationary wave. The two waves have the same frequency, have the same amplitude, but they are traveling in opposite direction. So which means that at one point, this point, we are going to have a point of zero amplitude, and also we shall have a point of zero amplitude. We shall have a point of zero amplitude and also another point of zero amplitude. So meaning the particles at this point where we have zero amplitude, it means that they are not vibrating, they are in the mean position. And these points where we have zero amplitude, we call them the nodes. And the point where we have maximum displacement, we call them antinodes. So all the points here, if you have a point at this, at this point, and you have another point here, and another point here, and another point here, all these points are in phase. But now let me just first focus on how to work out the wavelength of this stationary wave. So from here to this particular point, we have from this node to this node, we have a wavelength, and also here we have another half a wavelength. So meaning, how many wavelengths do we have from this point P to point Q? From here to this point gives us one wavelength, and this one is going to give us a wavelength. So meaning the total number of wavelengths we have in this part is 1.5 wavelengths. Because for standing waves, if you have a node and a node, this part here gives you a wavelength for stationary waves or for standing waves. 0.5 wavelength is spread through the length of the string, which is equivalent to 1.2 meters. So which means that we can be able to work out the wavelength of this wave and say wavelength is going to be 1.2 divided by 1.5. So if we work out this value, let's check what we're gonna get here. This is going to be 1.2 divided by 1.5. That translates to 0.8. That gives us 0.8, and then we're going to write it here, the 0.8 meters. That is the wavelength of this stationary wave. Now, on this one, we are told that there is a speaker that produces the sound, and the sound travels through, and we can see we have a node at this point. Also, we have a node here. Then at this point, we have antinode, we have antinode, we have antinode, and we have antinode. The node is a point where the vibration has zero amplitude, and the particles vibrate in maximum position at the antinodes. So you are supposed to calculate the wavelength of sound. Remember, in this question, we are told that the frequency of this sound is 1.7 kilohertz, and this sound travels at 340 meters per second through air, and through which sound is going to travel in this medium is air. So we're going to say the speed of sound through this tube is 40 meters per second. So meaning that sound is being produced by this loudspeaker, and then is going to travel. Upon reaching this point, is reflected back, and then superposition takes place for us to have a stationary wave. So which means that for us to work out this question, we are going to use the wave equation, and we know that the wave equation states that speed of a wave is equals to frequency times the wavelength. So which means that our speed is 340 is equal to the frequency. Our frequency is 1.7 kilohertz. So meaning this is 1700 hertz times the wavelength of the wave. So which means that wavelength in this case is equivalent to 340 divided by 1700. And if we can be able to put this in our calculator, we are going to get our answer equivalent to 0.2 meters as the wavelength of this sound wave. The next part is to calculate the length L of the tube, the length L of this particular tube. So we need to ask ourselves, how many wavelengths do we have in this particular setup? You see, we have a node, and this node is going to give us a half a wavelength, and then we have this is antinode. So meaning that this part here is going to be from a node to antinode, we have a quarter a wavelength. From when you have the distance between antinode and a node gives you a quarter a wavelength, and the distance between two adjacent nodes give you a half a wavelength. So between this antinode to this node, we have a quarter a wavelength, and from the node to this other node, we have a half a wavelength. So meaning that for us to know the distance between this antinode, how many wavelengths we have between this antinode and this second node, it will be 0.25 plus 0.5, and that translates to what? This translates to 3/4. This translates to, for this distance, we have 3/4 wavelengths, and those ones are spread across the length L. Now, in order to find L, already we know what the wavelength is at this point, and therefore we are going to say our L is equals to 3/4 times 0.2, which is equivalent 3/4 times 0.2, because that was our wavelength, and then we're going to get our answer as 0.15 meters.